It is now 10 past, so let's go ahead and get started. Today, we're going to first start by finally getting to estimating volume using MCMC, which I meant to do for the last, I think, 2 lectures, but it's just never gotten around to it because like something else got in the way. So we're finally going to actually use MCMC to estimate high-dimensional volumes. And then I'm going to briefly mention PageRank because it's one of the other super applicable examples of people using Markov chains in real life, because it was the basis at one point of like Google search algorithm. It probably no longer is. I don't know what they do now, but yeah, so I'll talk about those. And then instead, I'm going to take some time, and I have a PowerPoint prepared with like 50 some odd slides, where I'm going to do a really high level overview of a lot of different topics that we are going to cover in this class and that we aren't going to cover in this class. Basically because I want you guys to start thinking about, for those of you who are actually taking the class, I want you guys to start thinking about your final projects. And so I want to give an overview of all these different techniques. So you might find one that you think is interesting to help with like proposing a project. Okay, so let's go ahead and get started. So estimating volumes of convex sets. We're only going to deal with convex sets right now because it turns out non-convex sets are super duper weird, and it's really hard to do anything with non-convex sets, as anyone who's done any convex analysis will know. So estimating volume of convex sets. So remember, back in one of the early lectures, we showed that rejection sampling dimensions. So if you had some sort of ball and you were sampling and you had some object inside, rejection sampling would just involve taking lots of random points and seeing if they're inside of your polytope or whatever figure you have. And this fails in high dimensions because the ratio of the volume of the interior object goes to 0, since all the volume is on the surface anyway. So this was basically the result we had in, with these high-dimensional hyperspheres. You can't even do a rejection sampling of a high-dimensional hypersphere using a hypercube because the volume goes to 0. So rejection sampling fails. Sampling fails in high dimensions because the volume of the interior object, compared to the exterior, goes to 0. So obviously it doesn't actually go to 0, but for any particular object. So for any particular object in high dimensions, you could do some sort of rejection sampling, but the issue is that you would just be discarding almost all of your points with high likelihood. So what can we do instead? So instead, what we're going to do is, we're going to do something slightly more clever, if I can spell the word instead. Instead, consider a convex set. Let's call it R. And what we're going to do is we're going to choose a bunch of concentric circles. Choose concentric circles. And by circle, I mean hypersphere. Choose concentric circles, S1 through Sk, such that S1 is contained in R and R is contained in Sk. So basically, that looks something like we have some figure, we have a circle, and we keep on increasing the circle's radius until you capture all of your shape R. Okay, so that's R, and these are our SI circles. You can do this with rectangles instead as well. It doesn't really matter. Just some sort of figure where we know how to compute the volume. So we know how to compute the volume of a high-dimensional hypersphere. I mean, it does go to 0 as the dimension grows, but for any particular high-dimensional hypersphere, we can give its volume. Or for any particular hypercube, we can give its volume. Okay? So then what we're going to do, the overall strategy, is we're going to use rejection sampling. We're going to use some sort of rejection sampling type idea, except we're going to do it for each of these, for the ratios between each of these objects and the spheres that slowly grow. And so in any one particular step, not too many samples fail. And in order to be able to do that, we're going to have to be able to sample from these high-dimensional objects. So we know how to sample from a hypersphere, because that's something we covered. We know how to sample from a hypercube, but how do we sample from the intersection of a hypersphere and some arbitrary convex shape? Any ideas?
there's no easy way to check whether something is in the convex set or not.
Oh, well, then let's assume that we actually can check whether something's in the convex set. So you can do some form of rejection sampling, but yeah. So what we're going to do, though, is we're going to take advantage of Markov chain Monte Carlo, which is if you had some Markov chain that was wandering around in some set, in some shape, and for some fraction of that shape, it's the object that you care about, then you can just ask how long does the Markov chain stay inside of the smaller enclosed space. And so that's effectively you're sampling from this bigger space, and then you're doing some kind of rejection sampling on that. But in order to sample from this oddly shaped exterior, we're going to be using Markov chain Monte Carlo. So let's make that a little bit more precise. So first, we need to notice a few things. So the first is that the volume of R is equal to the volume of SK intersect R. Easy enough, right? SK includes R, so therefore the volume of the intersection is just the volume of R. What we can then do is we can telescope this out. So volume of SK intersect R divided by, this is equal to that divided by the volume of SK minus 1 intersect R times the volume of SK minus 1 intersect R divided by the volume of SK minus 2 intersect R, and so on, all the way down to volume of S2 intersect R divided by the volume of S1 intersect R times the volume of S1. Or more precisely, S1 intersect R. But S1 intersect R is, of course, just S1, since S1 is entirely contained within it. Okay, so we have each of these. So now what we've done is we've broken it up into each of these terms. And in order to compute the volume now, since we know this volume here, all we have to do is we need to compute these sorts of fractional ratios. How much of the volume of SK minus 1 intersect R, SK minus 2 intersect R is contained in SK minus 1 intersect R. So you have two convex shapes, and you're asking how much of the one convex shape is inside of the other. And the way we're going to do this is we're going to sample the bigger convex shape, and then we're going to say, well, how often are you inside of the convex shape that you care about? And so what we're going to do, note that if the radius of SI is 1 plus 1 over d times the radius of SI minus 1, well, then the volume of SI is going to be equal to 1 plus 1 over d times the volume of SI minus 1. Okay, easy enough. Did I get that direction right? SI is, yeah, okay. So this then implies that 1 is less than or equal to the volume of SI intersect R divided by the volume of SI minus 1 intersect R is less than or equal to 1 plus 1 over d to the d power is less than epsilon. Sorry, not epsilon, less than e. Wait a moment, I think I did something wrong here. I think there should be a d power there. Yeah, so there should be a d power there because obviously you're scaling. Yep. Okay, why is this? Why is this true? What factor are we making use of that this ratio is greater than or equal to 1? Yeah, so it's by the convexity of R and the fact that the larger circle is going to contain more of R, right? So clearly that means that the volume is going to increase. So this is by convexity of R. Of R. So the larger circle contains more of R. Actually, you don't even need convexity here. Like just the larger circle always contains, the larger circle just always contains more of R, right? Because it contains all the points that there were to begin with. Over here, this is where we need convexity. So note that, of course, that volume of SI intersect R divided by the volume of SI, this is less than or equal to the volume of SI minus 1 intersect R divided by the volume of SI minus 1. And this is by convexity. By convexity, And one way to see this, this isn't quite a foolproof, but if you have an object inside some circle, as the circle gets bigger, you'll notice that if you think about each of the rays going from the center of the circle out, well, let's say that, sorry, we need the center of the circle of the circles to be inside of our figure. If you start thinking about starting from rays here, if a ray is, each of these rays is either completely contained within the object or it's not. But as you increase for each ray from the origin, the fraction of that ray, which is occupied by the object that you're trying to, the convex object, cannot increase. And this is by convexity, because what you're saying is that as you look from the origin, as you go out, well, once you hit the boundary of whatever object it is, well, then after that, the ray is never going to contain any more of that object, by convexity. Whereas if it was non-convex, you could have some weird thing happening where the ray contains more of it. But so that's why we get this ratio here. And that's why we get this is less than or equal to the ratio of the two volumes of the spheres themselves. And so what this means is that this volume is something we can use rejection sampling for, because like not too much of it disappears each time, right? So each time you sample, you have a 1/e possibility of getting it right. And luckily, e is a fixed constant. I mean, one of the most fixed constants there is. And so therefore, you can actually do rejection sampling in this way. But basically, this means that if we can sample from lists, if we can sample from SI intersect R, then we can approximate. And approximate the ratio that we care about, volume of SI intersect R divided by the volume of SI minus 1 intersect R. We can approximate that volume by rejection sampling. Sampling, since accepted points are a greater than or equal to 1/e fraction of all points. Right, so the problem with rejection sampling is that in high dimension, you reject too much. And so you're basically doing tons and tons of samples that don't actually matter because they all get rejected. Now here we can say that if we're doing this particular rejection sampling, we only need to reject, well, at most a 1 minus 1/e fraction, which, yeah, it's not great, but it's some constant value, constant fraction. So then the next question is, how many spheres do we need? So like basically, what is the value of k here? Well, I mean, that's not too hard, right? Because that's just the ratio of the radii as you increase. And so that's going to be bounded by the radius of the outside. So like the ratio of the radii, because each time you're increasing by this multiplicative value of 1 plus 1/d. So the number of spheres needed, or circles. I keep on switching between spheres and circles. They're the same thing as far as I'm concerned. The number of spheres needed is going to be k is less than or equal to 2 times log of 1 plus 1/d times r, where r is equal to the radius of the big circle divided by the radius of the little circle, or the smallest circle, S1. Okay, and of course that implies that k is less than or equal to 2 log r over log of 1 plus 1/d, which is less than or equal to 2 log r over 1/2d. And this is by the log of 1 plus x is less than or equal to x and is greater than or equal to half of x fact, which is going to be equal to 4d log r. So if each ratio is estimated to an error of 1 plus or minus epsilon over 4e d log r, then we can estimate the overall volume to error 1 plus or minus epsilon. Okay, so basically, each time we have small error, then at most the error is just combined. And so this allows us to estimate the volume of an object without too much of an issue. So now, of course, the question is, how do we estimate these ratios? And that's where we're going to use Markov chain Monte Carlo. So let's see, how to estimate ratios. So what we're going to do is note that we have some object, say list, that's in some bigger object, not drawing these to scale. And what we're going to do is, let's say this interior object is Si minus 1 intersect R, and this exterior object is Si intersect R. Well, what we can do is we can just set up a Markov chain that's at each of the points of this grid. It's going to take me too long to draw all these points, but basically we have some grid and we have points in some Markov chain that we're defining based off of lists. So we have some grid. I'm done thoughting. So we have some grid, and we can just use Metropolis Hastings on it. Use Metropolis Hastings. Metropolis Hastings on this rectangular grid. And by rectangular, I of course mean rectangular in high dimensions. And have the stationary distribution. So we can define a stationary distribution that is uniform on all points inside Si intersect R. And remember, the way we did that for any undirected graph is we had some formula for whether or not the random walker walks from one point to another, based on the probability mass that we want to assign there. And basically what's going to happen here is the random walker is just is going to have some probability of going from one place to another. And when we look at the stationary distribution, that's going to give us a uniform distribution over Si intersect R. So this bigger thing. And then all we have to do is look at what fraction of those random walkers then end up after some amount of time inside our smaller circle, our smaller object. Okay, so and that's basically it. So the stationary distribution that is uniform on all points inside Si intersect R. So we just need a standard random walk. Need a random walk along the undirected graph with nodes in Si intersect R. And note that this has a high dimensional grid structure. And this isn't quite the same grid that we proved stuff about in the last lecture, but we did basically show that high dimensional grids, especially high dimensional convex grids, have fast convergence because we can bound the conductance. And I'm not going to actually prove it here for an arbitrary shape, because obviously every shape is going to have slightly different conductance. But this explains why you would expect to have fast convergence on these particular grids in the high dimensional space, is because, well, they're grids. And you have very similar properties to like the standard high dimensional grid that we talked about. And so we have fast convergence to the grid structure. Okay, and this is one of the many ways that people can use Markov chain Monte Carlo. And we're just showing here that you can apply this back to one of the problems that we had in high dimensions, which was estimating volume. And so using this method, if you have any convex shape, say some polytope, if you can tell whether a point is in that polytope or not, then you can run this method and you can estimate the volume of that high dimensional polytope. Okay, so that more or less ends our discussion of Markov chain Monte Carlo. If you continue in data science, I'm sure you'll see it in other places. It's often used whenever you need a particular probability distribution. And now I'm going to switch a little bit and talk about PageRank. So consider something called the World Wide Web. So it's going to be like some arbitrary collection of what we're going to call web pages, and they're going to have things called hyperlinks that a web surfer can use to walk from one page to another. Now, this is a really advanced concept. It was only developed a couple decades ago, but it's just a big network. You can think of it as where people walk around. Some of you may be familiar with it. So consider the, so often we refer to it as WWW, the World Wide Web of something called web pages. So now, if you think about this having this giant web of a bunch of different web pages linked together by these directed like arrows, you might ask, how do you find anything on such a big web of just knowledge? And now, luckily, people have thought really long and hard about this problem and invented something called a search engine. So now, what do search engines do? Well, if you're a search engine, you have two tasks that you care about. So if you are a search engine, you have two tasks. Well, at least two tasks. Some search engines have ballooned a little bit in size and do other stuff now too. But you have two tasks. One is find web pages containing a search term. Like if I want to know about cars, maybe I will type car into a search engine, and then it'll tell me all about these other web pages that contain the word car. But now that's not all you want to do, right? You might want to do a little bit more than just give me a list of all web pages that contain the word car. If there are a billion pages that contain the word car, then that isn't very helpful. The next thing you might want to do is you might want to rank them by importance. Rank by importance. So maybe some pages that contain the word car are more valuable than the page, some pages that don't contain the word, some other pages that contain the word car. And now this is like this nebulous idea of importance is a little bit hard to, it's a little bit hard to really quantify. So you could, in theory, have someone who just reads through every single web page on the internet, or the internet just being where the World Wide Web lives. So you could just have someone do that and then write down a score for every single one of your search terms and every single page, and you could use that. But that would take a really long time, and it would be quite expensive. Another thing you could do, though, is you can take these ideas that we've learned about from random walks. So like maybe a web surfer isn't being completely random on the internet, but there's a good argument to be made that you can sort of model someone on the internet as just a random process that's just randomly clicking things mindlessly. And if you were to do that, you would end up with a Markov chain. And we know some properties of Markov chains, right? So let's model a web surfer, that's someone who surfs the web, as a random walk on the hyperlinks. So now this isn't a perfect model because maybe people aren't completely mindless when they're on their internet, but it's good enough for our purposes. So you're going to model a web surfer as a random walk on the hyperlinks. Now, what's the first issue you might come across whenever you're thinking about this sort of directed edge, this directed network that we're going to call the World Wide Web? If I'm a random walker walking on a directed network, will I necessarily reach all the other pages? Yeah, so there's this issue that the World Wide Web isn't strongly connected. So remember we talked about that Markov chains being strongly connected, and the World Wide Web isn't necessarily that, because you might have some web page that no one really likes, and so no one links to it. And so there are no in edges, there are only out edges. Now, how do you deal with that? Well, the answer to that is, well, you can just add effectively, you can add some weak edges between everything. And so these are roughly modeled by someone just randomly starting at a different point. And every so often, they've been mindlessly clicking for a while, and then they're like, oh, I give up. I'm just going to restart somewhere else and then find some new web page that's of interest. And so you can do what people call random restarts. So this is not strongly connected, not strongly connected. So instead, we're going to add random restarts. And it turns out that when you add random restarts, then all of a sudden, the Markov chain becomes strongly connected, because at every point you have some probability of just restarting anywhere else on your network. And this allows us to get stationary probabilities. It's a little bit hard, like non-trivial to prove that this gives you the stationary probabilities, but you do actually end up with the stationary probabilities under certain parameter names. So add random restarts to give stationary probability distributions. These stationary probabilities are what we call PageRank. So these stationary probabilities are the PageRank. And what do they correspond to? They correspond roughly to this mindless web server, how long they're going to spend on any one of these, on any single web page. If a web page is one that a random web surfer would go to often, then maybe that means it's more important than a web page that people don't go to very often. So, and correspond to the frequency with which a page will be randomly visited over a period of time. And that's it. That's what PageRank is. So now you know one of the major innovations that Google had to start off with, which was that, well, it's really hard for us to know what's important, but presumably more important pages will get more links that come into them than that they have going out. And so they're going to have more probability mass from random people clicking around mindlessly on the web than a page that doesn't have that. Any questions? And of course, hopefully most of us are familiar with this thing called the World Wide Web, even if I was explaining it in a bit more naive of a way. Okay, so that basically ends my discussion of Markov chains. Like I said, you should ask any questions you have now, because we're about to take a world, in the remaining time today and tomorrow, because we're not going to get through all today, we're about to take a whirlwind tour through a bunch of different topics in data science, and I'll even mention machine learning and all that. So let's go ahead and switch over.